So I graded the fruit fly lab this morning, but I'm not sure if everyone got feedback, and we'll take the time to check. So I'm going to go through some ideas on here. Hopefully some of you can use that before the lab final 6th hour. So question 4, how can you physically tell male from female? Is the shape of the abdomen. The male had a rounder, less pointy abdomen than female. On the chromosome map, obviously you can look at if it has one X chromosome or two, but we wouldn't physically be able to see that on a fly. Why do the chromosomes come in pairs? And that's because they're homologous pairs, and we get homologous pairs due to two different parents. In the case of the male with the W gene for white eyes, it was on the X chromosome. That's an example of a sex-linked trait. And so if you chose a gene for your experiment from the X chromosome, it would be a sex-linked trait and not follow Mendel's monohybrid cross proportions. You would not have had statistically significant results. When you click on to make it a male fruit fly on the chromosome editor, you notice you lose an X chromosome. Males have one X. And then in order to get the female fly to have white eyes, you have to make both chromosomes with the recessive allele. If you set up an experiment with two parents that are heterozygous for a trait, in theory, you should get 75% the wild phenotype, 25% the recessive phenotype. And that fits the 3-to-1 ratio Mendel ended up with in his results. So that's what you'd be expecting. You would also expect that the parents would show the wild phenotype. So is the recessive phenotype shown in hybrid parents? It shouldn't, unless you're dealing with a codominant trait, which some people may have chosen, because there were some examples of that on the chromosome map for the fruit fly, or if you picked a sex-linked trait that you could have possibly ended up with. For example, if you pick the white eye gene in males, then they would show the recessive phenotype. Okay, interpretation. So we had some people come up with a critical value and a chi-square sum comparison, and there were some challenges with some interpretation for folks. So I wanted to clear that up, hopefully. I'm going to skip over to this. So basically what you're doing with the chi-square test is to see if two groups are statistically the same, or are they different? So ultimately you were testing your data against the expected data, Mendel's 3-to-1 ratio for the monohybrid cross. You would have expected 75 and 25 for your two phenotypes. Wild would be more common, recessive less common. If your values were, say, 76 and 24, or 77 and 23, you'd be really close to Mendel. And when you get your chi-square sum, it would be a small number. The critical value for two variables that you're comparing in the case of a chi-square test is 3.84. If your chi-square sum is lower than 3.84, then you are saying your data is similar enough to Mendel's to be statistically significant. So instead of using a p-value to determine your statistical significance, you're using your chi-square sum and comparing it to a critical value. Conceptually, it's the same idea as looking at your p-value and comparing to your critical threshold that you use for whatever percent you're looking at, whether it's 99% or 95% accuracy or confidence interval. But in the case of the chi-square, this is the number you compare your chi-square sum to, make a decision. So most of you had numbers that were lower than the critical value, which means you'd say, yep, statistically ours are the same as Mendel's. If you didn't have that, you may have chosen a codominant allele, or maybe you chose a trait that was on the X chromosome, sex-linked trait. If you have more questions, you can bring them to lunch. I'll probably have a working lunch answering questions right before class. So, hope this helps.